Good morning, students. We are just going to continue what has been where we have left in the previous lecture. So we have four different types of techniques which are available. Okay, under the unsupervised learning. Okay, one is clustering, anomaly detection, and then association rule mining, and we have dimensionality reduction. So under the dimensionality reduction, we have a principal component analysis and a DB scan, density based spatial distribution, autoencoders, and also have a association rules rule mind. Okay, so which we have seen this one up to in the last lecture. So we are going to see an example for all these four cases. Okay, the advantages. Okay, before getting into the examples of all these four categories, we will see the advantages of unsupervised learning. So no need for label data. Okay, useful for exploratory data analysis and also can uncover hidden patterns, structures in complex data sets. So this also I already told you in the last lecture. Okay, so I just go to the direct to the examples. So what is k-mean clustering? So catalyst performance classification. So example one, the scenario, you have an experimental data from multiple catalysts tested under similar reaction condition. So for example, you have a reactor. So I have a feed flow rate, okay, as well as the temperature and pressure which has been maintained in the reactor. But what I'm going to do, I'm just going to vary the different types of catalyst and try to identify how much is the yield. Okay, so the parameter which I'm going to adjust is only the catalyst. The other parameters like the concentration of the reactant or the flow rate or the temperature, pressure which has been maintained inside the reactor, I'm not going to vary. So we have experimental data from multiple catalysts tested under similar reactor condition. That's why please underline the word under similar reaction condition. So in that case, use of k-means. So we can go for a k-mean clustering. Cluster the catalyst based on their features. So what are the features of the catalyst? It may be a conversion efficiency, selectivity, and stability to identify the high performing groups. So they cluster the catalyst based on the features like conversion efficiency, selectivity, and stability. Okay, so to identify the high performing groups. So this is an example for k-mean clustering. The next example for batch process monitoring, the scenario analyzing the historical data from multiple batch runs in a reactor. So you just try to identify the data which has been obtained from the different batches, okay, of the reactor and try to analyze the thing. Use of k-mean distribution clustering, cluster the batches based on the key parameters, that is a temperature, pressure, pH, yield, to identify typical operation pattern versus deviation. So you could know actually do different multiple runs and then try to observe the data. So this is under which k-mean clustering. This is also a very good example. Okay, coming to the hierarchical clustering. So the example one, classification of chemicals based on the properties. So grouping a database of chemicals based on physical and thermodynamic properties. So you know the thermodynamic properties. Okay. So physical properties is like boiling point, molecular weight. Okay. So polarity. Okay. So ours the thermodynamic properties like what you called enthalpy, entropy. Okay. Specific heat capacity. Okay. Grouping a database of chemicals based on the physical and thermodynamic properties. That is a scenario. Use of hierarchical clustering. Create a dendrogram. So which I already shown to you in the last lecture. So how the dendrogram looks like. It's a tree-like structure where the nearby clusters have been combined. Okay, so by combine with that and then form a single cluster. Okay, create a dendrogram to visualize the similarities and classify the substance into families. So the families is a groups. Okay, it is like FTR is used to find functional group, right? So the functional group, identify the functional group will segregate the compounds. For example, alcohols, okay, OH, ketone, okay, acids, COH, okay, ketone is C double bond O, aldehyde, CHO, okay, so and amines like NH2 or NH3, okay, so these are the things. So how to classify the compounds, create a dendrogram to visualize the similarities and classify. So this is coming under the hierarchical clustering. So coming to the example, another example for hierarchical clustering, heat exchanger fouling pattern analysis. So as we know, the fouling is very common in heat exchanger. Okay, monitoring the fouling tendencies across multiple heat exchangers in a plant. So you have multiple heat exchangers, try to find the fouling tendencies. So in that case, we can go for a hierarchical clustering. Group heat exchangers with similar fouling behaviors based on the time series dependent drop, temperature drop and pressure drop. Time series, temperature drop and pressure drop. So if you have a different types of reactor heat exchangers in your industry and try to identify their pattern, how the fouling pattern occurs, okay, from different types of heat exchangers. Okay, group heat exchanger with a similar fouling behaviors. Okay, so in that case we can go for a hierarchical clustering. And DB scan, density based spatial distribution, spatial clustering, okay, of application with noise. So in that case is an anomaly detection in sensor data. Okay, so the continuous monitoring of reactor temperature and pressure via IoT scan sensors. Okay, so identify the normal operating conditions versus the outliers indicating the abnormal or hazardous behavior. So density based spatial clustering of application with noise. So it's coming under the example for anomaly detection in sensor data DB scan. Okay, so please try to understand. Okay, this is an example for anomaly detection example for DB scan. And similarly, the spatial distribution of particles in fluidized beds, the scenario studying the particle distribution patterns from simulation data in fluidized bed reactors. So use of DB scan cluster region of dense particles agglomeration and detects sparse zones or voids as noise or anomalies. Okay, so we are just given example for each category. So you just try to understand with the chemical engineering background. Okay, where and all how the data need to be can be categorized. Okay, under which category? Okay, so we have a four categories under supervised and unsupervised learning. Okay, so one is a K clustering, and then anomaly detection, dimensionality reduction, as well as the mining. How do you call it, the mining. Okay, so please try to understand this concept. Okay, so which category we need to go for the based on the our scenario, okay, our requirement. And principal component analysis, so usually it will go for a spectral data, FTIR, NMR, Raman spectroscopy. Okay, so spectroscopic data analysis, the scenario is you have hundreds of spectral intensity readings across many wavelengths for a set of chemical samples. Okay, so in that case, use of principal component analysis will help you to categorize the data, reduce the dimensionality of the spectral data while retaining the most of the variation, identifying sample grouping, detect outliers, simplify classification task. So the use of principal component analysis is identify the sample grouping, detect outliers, and then simplify the classification task. And coming to the second example for principal component analysis, a scenario for this case is a chemical process with 30 to 40 sensors. Okay, generate a large data sets. Okay, so reduce the number of variables to a few principal components that capture the most significant variation. Okay, helping with visualization, monitoring, and early fault detection. So, why we need to go for principal component analysis? Reduce the number of variables. So, principal component analysis is a reduction. What do you call it, the anomaly detection and variation, I mean reduction in the dimensionality reduction. Okay, so reduce the number of variables to a few principal components. So number of variables to a few principal components that capture the most significant variation. Okay, so that is the advantage of going for this type of dimensionality reduction. Okay, so helping with visualization and monitoring and early fault detection. And coming to the TSNE, that is a T distributed stochastic neighbor embedding. So the example is visualizing the operating modes in a chemical plant. The scenario, time series data from various process states, startup, steady state, shutdown, or step condition, you already know. So time series data from various process state. So if you have a reactor, okay, if that reactor is running, startup how it behaves, at steady state how it behaves, during the shutdown how it behaves, upset condition, if there is any fluctuation or any deviation, okay. So in during or troubleshooting, upset condition is a trouble. I can put a good word called troubleshooting. During this period, how the system behaves, the process condition, the state behaves. Okay, the time series data from various process state. Okay, so in during that period, how it behaves. So in that, this is an example for T distributed stochastic neighbor embedding. Use of TSNE, that is a stochastic neighbor embedding. Project high dimensional data into project high dimensional data into 2D or 3D visualization to visually identify the clusters of different operating modes. So TSNE will help you to project the high dimensional data into 2D or 3D to visually identify the clusters. So in that case, we can go for TSNE. Okay, so this is all coming under which categories actually? So is all coming under the anomaly. What you call it? It's not anomaly detection. It's a principal component. Dimensionality reduction. Okay. So TSNE, we have seen an example, and autoencoders. So example is noise reduction in sensor data. Okay. Real-time data from chemical plant sensors often contains noise. So in that case, train an autoencoder to learn the compressed clean version of the signal and reconstruct it effectively, filtering out the noise. So autoencoders is a very good example, okay, for this category, okay, for this scenario. And coming to the another example for autoencoders, latent feature extraction for reaction monitoring. The scenario is high frequency time series data from a reaction process. So you have a temperature, pressure, concentration, okay, high frequency time series data from a reaction process. Okay, so we can go for a autoencoders. Use of autoencoders extract the meaningful latent features like low dimensional representation that summarize the system dynamics for use in predictive modeling or anomaly detection. Okay, so autoencoders, okay, it will also help you to extract the meaningful latent features, okay, that summarize the system dynamics for use in predictive modeling, okay, for use in predictive modeling. So this scenario is something like this: high frequency time series data for a reaction process. So we need to collect a lot of data actually during this process. High frequency time series data for a reaction process. We need to collect the temperature and pressure. I would like to share my experience during my internship where I have been asked to collect the temperature of for every 5 minutes, okay, near to the reactor. And despite they have a control room, they are monitoring the temperature and pressure inside the reactor. But we have been asking to note down these two parameters. Okay, so every 5 minutes they will try to collect. So we'll if there is any going beyond the normal condition, it will be easy for them to identify the things either by control room or by physical reading. Okay, so why they are doing? They are not. I mean, during that time, almost 20, 25, 22 years back, the people are the control room. Despite they have a reading, okay, they will also monitor what is called manually as well. Okay, if there is any malfunction of the sensors or any problem in the control room, okay, so if they don't trust the thing, so they also capture the data from the manual means. Okay, so high frequency time series data from a reaction process. So in that case we can go for autoencoders in order to extract the meaningful latent features, okay, low dimensional representation that summarize the system dynamics for using predictive modeling. Okay, so hope you understood the use of autoencoders. Okay, and coming to the isolation forest, this is another category. Okay, isolation forest works by randomly selecting features and split values to isolate the anomalies quickly. So this is coming under the anomaly detection. Okay, so dimensionality detection where principal component analysis. Okay, autoencoders. Okay, here we are getting into the third part of the unsupervised key parameters of unsupervised learning. That is a anomaly detection. The anomalies are more susceptible to isolation because they are rare and different. Okay, so anomalies are more susceptible to isolation. So this type of data need to be keep it separate. Okay, this is not even commonly occurs. Hope you understood what I'm trying to say. Anomalies are more susceptible to isolation because they are rare and different. Example is yearly fault detection in heat exchangers. So the scenario is going like this: monitoring the temperature and pressure drop across multiple heat exchangers. So the temperature and pressure drop is maintained, is monitored across multiple heat exchangers. So use of isolation forest. Okay, use of isolation forest detect the unusual heat transfer performance that may indicate the fouling or leaking. Okay, so that means the heat transfer is not effective. Obviously, this may be occurred because of the some of the factors like fouling or any leaking. Okay, or maybe the different fault. Okay, so this will help you. This will rarely occur that isolation forest. So this is one example use of isolation forest in a where the anomaly is used to is identified. Okay, that means deviation from the normal data. Hope you understood. So coming to the second scenario for isolation forest, detecting the sensor failure in chemical reactors. So just now I told you they don't behave. The even when I was in internship, I have been asked to measure the temperature and pressure of the reactor, even though they have the control room. So detecting the sensor failure in chemical reactors. Okay, the scenario here is continuous reactor monitoring, like temperature and flow rate annually. Okay, use of isolation forest. Identify the sudden unrealistic sensor reading that could indicate the sensor drift or failure. So if we have find any not common unrealistic sensor reading that could indicate the sensor drift or the failure of the compound, or maybe occurs because of the some unwanted process conditions. Okay, so one class support vector machine. So this method learns coming under the anomaly only, anomaly detection. Okay, so the example, the quality control in polymer production. The scenario goes like this: using features like viscosity, molecular weight, and process condition. Use of one class support vector machine flags batches with the abnormal combination of these parameters that may lead to the product defects. So when you have this condition, okay, for example, I want a low viscous and high molecular weight compound or something. Okay, if it is going in the other way, obviously that will lead to a unwanted product. Okay, flag batches with the abnormal combination of these parameters that may lead to the product defect. Okay, because why I am trying to say this product is not having a not required quality. Okay, so I could also share during my internship. Okay, where I was working as a intern. Okay, for a paint industry, they try to produce the raw material for the paint. So the product which they obtain, they will test the quality of the product. So let's say you have humidity. Okay, the humidity. If they have the humidity is very large, there may be a agglomeration effect after the packing. So they will try to test the humidity of the product. So they will do the drying. Okay. So similarly, when you have try to find the quality is not up to the standard or thing, obviously that leads to the what you called uh, low quality. So we will try to find these features which is not effective or a deviation anomaly, that is deviation from the requirement. Obviously that data need to be collected. So this is one example. They say quality control in polymer production. The same thing I told, actually the quality control of raw material of the Asian paint. Okay, so that is a pentaerythritol. They also have tested the quality and they try to identify the things. But in this type of data which will help you to identify and the quality in a prior information will be given to the system so that we can understand. So if this type of data comes, actually obviously that is not the quality control is going down. Okay, so hope you understood what I am trying to say. So this use of one class support vector machine. Okay, in that cases we can go for this category is anomaly, is coming under the anomaly detection techniques. Okay, and coming to another example is detecting the abnormal reaction behavior. So the scenario is for this case is in exothermic reactors, unexpected spikes in temperature and pressure could signal runaway reactions. So use of one class support vector machine learns normal process behavior and detect the deviation yearly. So the main advantage of support vector machine, okay, deviation and detect the deviation yearly. Okay, underline the word detect the deviation yearly, learn normal process behavior. Okay, so in exothermic reactors, unexpected spikes. So exothermic heat is liberated. Unexpected spikes in temperature and pressure could signal the runaway reaction. So if it is very high, okay, so whether the reactor could be able to withstand that particular temperature, that also we need to look into the things, and we need to have a learn the normal process behavior from the system and detect the deviation early itself by using the own class support vector machine. Okay, so this is the anomaly detection. So the four categories: the clustering, detection, what you called going back to the previous thing, anomaly detection and data mining techniques. Okay, so these four categories are very important in order to understand the unsupervised learning. I just quickly go through the again from the beginning. Okay, so from the beginning, in the sense of the 4 points: the clustering, dimensionality detection, anomaly detection, and association rule mining. So the clustering, again we can classify the under this type, or dimensionality detection, okay, anomaly detection, and association rule mining. These are the four techniques. We will try to understand the unsupervised learning for this case, and with the chemical engineering examples we have seen each category, the three category which we have already seen. One is clustering, dimensionality reduction, okay, and then anomaly detection, okay, dimensionality reduction and anomaly detection, and the fourth one, mining techniques. So the support vector machine is coming under which category actually? So it's anomaly detection. Okay, and the statistical threshold, z score, IQR, moving average control chart. So the statistical thresholding based on the classical flags data points that are too far from the average or expected range. So it's a away from the data. So it's a skewed data, or we can say is an anomaly or outliers. So outlier detection in process yield. So is again anomaly detection. This is an example scenario: monitoring the product yield from a separation column. So use of z score or IQR. Okay, flags yield values that deviate significantly from the historical trends, signaling a possible tray flooding or feed change. So if it deviates significantly from the historical, signaling a possible tray flooding or a feed change, or the quality is getting reduced, as I told you, as I seen in the previous case regarding the support vector machine. Okay, so outlier detection in process yield is where we can go for a statistical thresholding method. Okay, so based on the classical statistics flags, statistics flag data points that are too far from the average or expected range. So the another example, anomaly detection in utility consumption. Okay, scenario: steam or electricity usage across different process unit. Use of control chart detects abnormal increase or decrease, indicating the potential leak or equipment inefficiencies. Detect abnormal increases, okay, or decreases. Abnormal increases or decreases, indicating the potential leak or equipment inefficiencies. So in that case, the deviation. So in that case, we can go for a statistical threshold. Okay. So this is a fourth category: mining technique, a priori algorithm. Okay, we have just come to the fourth part of the example. Okay, so in that case, which I already discussed, if A occurs, B is likely to occur, which I told you. The a priori algorithm identifies the frequent item sets and derives association rules using support and confidence thresholds. For example, if the pressure increases, obviously the temperature will increase. So the use of a priori finds rules such as if high agitation speed and low pH, okay, so hydrogen ion concentration, pH hydrogen ion concentration, then the product failure with high confidence with high confidence. So if this is happen, this definitely will happen. Okay, so is that category? I mean, is A happens, B likely to happen. Okay, so the scenario for this case is historical logs from multiple batch runs include events like high temperature, low pH, high agitation speed, and product failure. So using this algorithm, we can try to find it out, helps engineers identify and avoid combinations that lead to the poor outcomes. So for example, when I was doing my PhD in spray drying, and the humidity increases, I mean the moisture content increases for the spray dried powder, obviously it may lead to a agglomeration. The yield will be decreased because it will lead to a stickiness on the inside of the spray dryer. So if we have that category, we can go for a priori algorithm. Okay, if the spray drying, the particles having a moisture content is higher, obviously that will reduce the product yield. Okay, because of the stickiness on the surface of the spray dryer. So we can go for a priori algorithm. Similarly, you just think of your own cases where you have come out with a different lab experiment during in chemical engineering. So you could understand which categories we can go for. Whether we need to go for tape clustering or anomaly detection or dimensionality reduction or mining techniques. Okay. So the under which you need to identify the cases. And second example for a priori algorithm, process along correlation analysis. So the scenario is like this. So you can also have different scenarios, and which scenario will for your scenario, which algorithm will help you to understand the unsupervised learning. Okay, if you have a not a correlation data between the input and output. Okay, you need to think of. So a large chemical plant logs alarms triggered by process condition. Example: pressure high, flow low, temperature spike. That is the increase, sudden increase in temperature. Use of a priori: identify the frequent alarm sequence, like if pressure high, flow low, then shutdown triggered. Okay, enables preventive control action to break the chain early. So if you have this category, if the pressure is high, flow is low, then trigger them to the shutdown. Okay, so this will avoid the unwanted scenarios that is happen. So the a priori algorithm, a large chemical plant log alarms triggered by the process conditions, like pressure high, low flow, and sudden increase in the temperature high. So some cases the sudden increase in the temperature high may leads to the product quality. So in that case, we can go for the a priori algorithm. Okay, and FP growth. Okay, so is again a fourth category. Another two examples are there. With this, we can conclude today's section with the third subdivision of unsupervised learning. Okay, so coming to the FP growth, FP growth is an efficient algorithm for mining frequent item sets without candidate generation. Okay, often faster than a priori. So this is more faster than the a priori. FP growth is an efficient algorithm for mining frequent item sets without candidate generation. Okay, so let's see the scenario. The scenario goes like this. Process records show combination of solvent, catalyst, and additives used in the reaction. Process records show combination of solvent, catalyst, and additives used in the reaction. Use of FP growth. If solvent A and catalyst B are used, then the corrosion issue occurs. So if A occurs, B possibly occurs. So if this A and the solvent catalyst B is used, obviously the corrosion occurs. So this will not be useful for improving the material selection and preventing the equipment damage. Most of the time in the extraction technique, we may not be knowing actually how to choose a correct solvent. Okay, obviously we know this depend on the solubility and the polarity of the compounds. Okay, we need to choose the solvent. But if they have the same categories, okay, then which one is better, or which one need to be avoided? So by using this FP growth algorithm, we could be able to very well can identify, okay, which one is the better. Okay, useful for improving the material selection and preventing the equipment damage. Okay, so if you know the combination, then it will be easy for us to segregate the thing. Okay, so this algorithm FP growth is very comparable, is more often faster than a priori algorithm. Okay, so please try to understand the thing. Okay, so process records show combination of solvent, catalyst, and additives is the scenario over here. So this is an example for identifying the material compatibility issues. And coming to the FP growth, another example is the utility optimization in chemical plant. The scenario is historical data on utility consumption. Example: steam, cooling water, electricity, and operational setting. So use of FP growth algorithm. So identify the rules such as if the reactant set point is high and the cooling rate is low, then high electricity usage. So when we need to go for, obviously we need to go for a low electricity usage. So this point is not needed. Else optimize the utility usage or the material selection. In the previous stage we have just used the material selection. Here the optimize utility usage. So in that case, we can go for a FP growth algorithm, that is a frequent pattern growth. Frequent pattern growth. FP growth is a frequent pattern growth. So hope you understood. So I have given many examples for chemical engineering perspective for unsupervised learning, under which we have 4 different algorithms. Okay, where we have dimensionality reduction, k-mean clustering, and anomaly detection, as well as the mining techniques. So association mining techniques. Okay, so with this I just try to conclude this section, today's section. So if you have any doubt or anything, just please feel free to ask me, and try to understand, create a different types of scenarios among yourselves doing the chemical processing, as you are very well aware of how the chemical process occurs, and you have a background and domain knowledge on the chemical engineering principles. Okay, so in that case, which type of algorithm will help you if you don't have a relationship between the data, input data and output data. So with this, I would like to conclude my section. Okay, if you have any doubt or anything, please feel free to ask me. Okay, thanks for listening. Thank you very much.